Hey, all right, good morning. It's been a little bit since we've had some videos here for class, so please excuse me if I make a mistake here at any point. But today, while you guys are doing remote learning, you're going to talk, or you're going to look at this notes section, hopefully copy this down. We're going to look at linear and exponential equations. So now at this point in your Algebra 1 career, you have already gone through both linear and exponential equations. Okay, so just as a quick reminder, linear equations, we're talking about like your y equals mx plus b, right? So you got your slope, okay, and you got your y-intercept or your starting value, right? And then exponential functions, you got y equals a times b to the x, where this is your y-intercept, and then this is your growth factor. Okay, or like we just had, if you get a rate, it's going to look like this instead. 1 and then plus or minus the rate to the x, okay? So you got your exponential functions here, you got your linear function there. Okay, so let's take a look at a couple examples here. We're going to go through our learning targets, just trying to be able to look at exponential functions in real-world situations. So example 1, Emily is a college student who plans to spend a summer in Seattle. She saved $3,500 for her trip and anticipates spending $400 each week on rent, food, and activities. So the question is, what type of model is this? So when we say that she saved $3,500 and she's spending $400 each week, is that multiplying or adding and subtracting? If it's adding and subtracting, then we're talking about linear. Multiplying, we're talking about exponential. In this case, it is linear. So what equation would best represent her situation? Well, we have our y equals, so our slope is how much it's changing, right? Well, in this case, each week, keyword being each, okay? And then you also have $3,500 and $400, okay? Each week, though, is your slope, so that tells you it is $400 for your slope. But since she is spending that, it is negative $400. Okay, and she saved up $3,500 to start. So that would be her starting value. Okay, so she plans to stay from June through August. Will she have enough money saved to pay for the entire trip? So we're going to run this equation and see if it comes out to be positive, then we know that she's got some money left over in the account. If it's negative, that means she has not saved up enough money to cover all the expenses. So if y equals negative 400, and we're going to say it's 13 weeks, so we're going to plug that in and solve. So 400 times 13, let's see, is 13 times 4, 2652. So this is negative 5,200 plus 3,500 gives us a negative $1,700. So to answer the question, will she have enough money? No, she will not. Okay, because this is negative, and that's her leftover. Okay. Example 2, Zane just finished college and began a new job. He currently has $10,000 saved in his savings account that he's going to start investing. He plans to take 10% of his remaining balance each month to invest while working in his new career. So what type of model is this? Okay, so it gives you a rate, and it's saying each month, but the key factor is here it's of the remaining balance, right? So that makes this exponential. Okay, so what equation would best represent this situation? Well, he has an initial balance of $10,000, and he's taking out 10%, which can be changed to this decimal. 10% every month. So X here is going to represent the number of months. Okay? So how much money will be left over after 4 months in the savings if he adds no money to that account from his new job? How much has he transferred to the investment accounts? Okay. So this is a two-parter. So let's go ahead and use Desmos and plug this in. So 10,000 minus 1 minus 0.10 to the 4th power, because that's how many months. Plug that in the notability, Desmos. So 10,000 times 1 minus 0.10 to the 4th power. And that tells you he is left with $6,561. So the question is, the second question is, or the second part says, how much has he transferred? So this is part A. And then how much has he transferred? Well, $10,000 minus your 6,561 tells you that he has transferred $3,439 into investments. Now, I'd love to see what he invested in and see if he's made that money back, or if it's actually a lower amount, but we will never know. Okay, example 3. A town's population has been growing linearly. In 2004, the population was 6,200. By 2009, the population had grown to 8,100. Assume that this trend continues. What type of model is this? Well, it actually says right up here, this is linear. What equation would best represent the situation? Well, there's a tough part with that. Remember up here, we had the slope of how much it changed each week. In this case, we do not initially have the slope, right? Even if we count 6,200 as our starting point, okay, we have no rate of change here. But as you look, 2004, 6,200, well, that's a coordinate point, right? So is 2009 and 8,100. So a little trip to the memory bank here tells us that in order to find the slope of 2 points, you take the second y value, subtract it from the first, and or the opposite of that, right? So in this case, we're going to take 8,100, subtract 6,200, and then we're going to take 2009, subtract 2004, and that gives us, let's see, what is that, 1900 divided by 5. 1900 divided by 5 gives you $380. So that is the slope, 380. So now the question becomes, predict the population in 2013. Well, if we know our now formula, from 2004 to 2013, that is 9 years. So if we say that this is our starting value, so after 9 years, we just plug in the 9. Right, because 2013 minus 2004 is 9. Okay, so times 9 gives you 3,420 plus 6,200 gives us a total population in 2013 of 9,620 people. Okay, so there's another linear problem. All right, and then last but not least, okay, a bacteria has been growing in a culture and examined over the last 2 days. The initial population was 25,000, but quadrupled every hour. What type of model is this? Well, it's quadrupling, so that would be exponential. What equation would best represent the situation? Well, we start with 25,000. And it's quadrupling, so that's times 4 to the power of x. Okay, so remember that this is every hour. So it says, what was the bacteria population after 10 hours and then after the first day? Well, after the first day is 24 hours, right? So we're going to plug it in twice here. So y equals 25,000 times 4 to the 10th hour and 25,000 times 4 to the 24th hour. Let's see if we can get some actual numbers here. These might be kind of big, huh? 25,000 times 4 to the 10th. Yep. So this is 2.621 144 times 10 to the 10th power. So about 26 billion. 26 billion. Okay, let's try it again. 24th hour. Woo! What's the name of a number that has that has 18 zeros in it? I'd have to look it up myself. I would not know. So we're going to say 7.04 times 10 to the 18th power. That's a lot of bacteria. That's a lot, right? But that's after 24 hours. It just kind of shows you how quickly this culture is growing. Okay. What's left for you? Just an exit ticket. 2 questions. Word problems. You're going to label whether they are exponential or linear. Okay, write down their equation and then solve the answer that it asked for. All right, good luck. Let me know if you guys have any questions.